We're asked to find the interval of which f is increasing or decreasing, the local maximum and minimum values of f, and the intervals or concavity at the inflection points. And we're given the equation f of x equals 2x cubed plus 3x squared minus 36x. So the most important thing here to note is that the derivative of the function will tell us the slope. So in order to find the intervals of increase and decrease, all we have to do is find where the derivative f prime of x equals a positive value, or the derivative of f prime of x equals a negative value, because that's going to be slope. It's going to be telling us increasing and decreasing. So in order to do that, we need to figure out where our slope changes. And the most important thing to remember is critical points, because the critical points are, remember, when the derivative is not defined or equals 0. And that's where the slope of the equation will change. So all we have to do to begin this question is to find the critical points. So let us do that. Alright, so we are going to take the derivative of this equation. So we have f prime of x equals, so we know the power rule, 6x squared plus 6x minus 36. Bring down the power, multiply it, minus 1. So, and now we're solving this equal to 0. So now we have, what I would do is factor out 6, x squared plus x minus 6 equals 0. I guess I don't need that. And then what we're going to do is we're going to solve for x. And so what we're going to get is 6 times x plus 6. That's going to be plus 3 and x minus 2. So now by solving it, we get x equals negative 3 and x equals 2. So these are our critical points, right? X equals negative 3 and x equals positive 2. With these critical points, we now know where our slope will change, because this is where the derivative is going to equal 0. Now remember, like, the derivative equals 0, if we have like a graph like this, the derivative is going to equal 0 at like a point right here, a local maximum and local minimum. So local max and local minimums are always going to be have a slope of 0. So now that we have our answers, our critical points, we can use these points as intervals and plug in numbers to see where our derivative changes from positive to negative. So I'm going to make a little chart and I'll be back to you in a bit. So here's our chart. We have negative infinity to negative 3, negative 3 to negative 2, and 2 to infinity. So all we're going to do is we have to plug in numbers from these intervals into this equation, and we'll get our value, our positive or our negative value. So you just do that. So all we're going to do is plug in values from the intervals into those given equations and see what kind of sign we get out of it. And from those signs, we can figure out if the entire derivative, by multiplying it together, is going to be positive or negative, and therefore if the original function is increasing or decreasing. So it's in two negatives make a positive, positive and negative make a negative, and positive, positive make a positive. That tells you it's increasing, decreasing, and then increasing. If we make a sign chart right here, which is basically a way to visualize things very roughly, we could see that there's a local maximum at negative 3 and a local minimum at 2. And therefore, we write down there's a local maximum of negative 3. We plug negative 3 back into the original equation, get 81. And there's a local minimum at 2. And plug that into the calculator, and we'll get, should be negative 44, right? And then the intervals of increase and decrease is already right there, so we just write it down in a complete sentence. The interval of increase is negative infinity to negative 3 and 2 to infinity, and the intervals of decrease is negative 3 to 2. And that is the first part and second part of the problem done. So now we're asked to find the intervals of concavity and inflection points. Now concavity and inflection points is actually very similar to increasing and decreasing intervals, because if you remember, the second derivative tells us concavity and inflection points. it tells us concavity by if it's positive, it's concave up, and if it's negative, it's concave down. So all we have to do is do basically exactly what we did for first derivative for our second derivative. So we're going to have f double prime of x equals the same rule, 12x plus 6, and everything else deleted because that's a constant. And then that's going to be, if we solve for this as x equals 0, we have 12x, so take out 6, that's going to be 2x plus 1 equals 0. And if we solve for that, we're going to get x equals negative 1/2. So this is going to be our inflection point. So we could say x equals negative 1/2 is our inflection point. And in order to complete that, we would plug it back into our original equation. So let us just do that really quickly. So now that we found our inflection point, all we have to do is find intervals of concavity. And all we have to do is set up the same chart that we set up last time, but for this point right here, the negative 1/2. So this is going to be f is concave down. F is concave down on the interval negative infinity to negative 1/2, and f is concave up on the interval negative 1/2 to infinity. And that is how you answer this question. So now we're going to talk about something a little different, and this is the mean value theorem. And the mean value theorem is pretty simple and just states that on a closed interval there exists a point where the derivative is equal to the slope of the two endpoints. So what that means is if we have a graph that's like this, the slope right here, in order to achieve that slope, we need to have a slope similar, actually identical to the slope right here. So right here it'd be right there. You see that? That's what it would look like on a graph. So in order to find this in our equation, we're going to use the same equation that we've been using, and all I'm going to do is plug in, this is just slope basically. We're going to find slope first. So this is just basically plugging in this value. So we're going to plug in negative 2 to our original equation. And this should get us, pretty sure we did this, but I do not remember it. 68, no, we didn't do this. 268. And now we are going to plug in our 2, plug in 2. And that will get us, I'm just using a calculator, negative 44. So these are our points, and all we have to do is do the slope formula. So y2 minus y1 over x2 minus x1. Doesn't matter which one's y2, y1, it just matters that you keep it consistent. So we're going to do 68 minus negative 44 over, and this is going to be 68, so negative 2, and then that's going to be negative 2. So this is going to be 68 plus 44, because negative minus a negative is positive, so 112 over negative 4, and that's going to get us negative 28. So now that we have our value of negative 28, we need to find our first derivative, or really just our derivative. And we already know that. It's going to be 6x squared minus plus 6x minus 36. Yes. And we have this equal to negative 28. So now we have to solve for x. The easiest way I can think to do this is move 28 to this side. So plus 6x, move 28, so negative 36 plus 28, and that's going to be negative 8. And so now we factor out, now we can only factor out 2. That's going to be 3x squared plus 3x minus 4. And from here, we could solve this in a variety of ways. I'm just going to use the quadratic formula. So we get, and I apologize, this is not a pretty number, but we will get with our, using the quadratic formula, because I chose to use the quadratic formula, this is not a perfect number like I thought it would be, and we get c equals negative 3 plus square root 57 over 6, or c equals negative 3 minus square root of 57 over 6. By the way, this c is just how we define the mean value theorem, a point. It exists a number c between a and b, so that's why I say c equals. That satisfies the mean value theorem. This is, if we drew this on a graph, it would look something like, well, point. This is going to be a very rough sketch, but it's something like that, where our slope right here is going to be like that and like that.